Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we're joined by Kyle Story, computer vision engineer at Descartes Labs. Kyle and I caught up after his recent talk at the Google Cloud Next conference titled How Computers See the Earth, a machine learning approach to understanding satellite imagery at scale. Kyle and I discussed some of the interesting computer vision problems he's worked on at Descartes, including custom object detectors and the company's GeoVisual Search engine. We cover everything from the models they've developed and the platform they've built to the key challenges they've had to overcome in scaling them. Enjoy. All right, everyone. I am on the line with Kyle Story. Kyle is a computer vision engineer at Descartes Labs. Kyle, welcome to This Week in Machine Learning and AI.
Thank you so much for having me on. How are you?
I am wonderful. You are joining an esteemed group of physicists who have been on this podcast. It seems like there are quite a number of folks that come out of cosmology like you and astronomy and particle physics and make their way to machine learning. Well, how did you do that?
Yeah, it's actually a fairly natural transition. So my background is in cosmology, as you said, which is a branch of astrophysics. And so I spent almost a decade in graduate school and then as a postdoc at Stanford working with data from a telescope that's in Antarctica, where we were measuring what's called the cosmic microwave background. So this is radiation left over from the Big Bang. Sort of, you can think of it as an afterglow of the Big Bang, and you can actually map it. And what you see in those maps are basically a baby picture of the early universe, or variations in density about 100,000 years after the Big Bang. And it's the furthest back you can see in time. And so I spent a decade studying this using the information and the statistics in those data to try to understand the universe as a system, model the universe as a whole. And then relatively recently, this past fall, I came out of academia to join Descartes Labs. And basically, instead of looking upwards using a satellite, using a telescope on the ground. I kind of inverted that problem. So I'm now using data from satellites to look downwards at the Earth. And so there are a lot of similarities and a number of important differences as well. So in one sense, they are both remote sensing problems. So they are both trying to learn something about phenomenon purely based on the light that you see or the signals that you're receiving from that source. And then on the machine learning side,
before we go too far, I've got to ask: did you ever get to spend time in Antarctica? Like, I'm envisioning, I forget the movie, but like the one camp where you go basically under, I don't know if it's underground, probably not under ice, but you go into this encampment. Was it anything like that?
It's not quite like that. I have spent just shy of a year of time total in Antarctica that was spread across 6 different trips. So that the telescope that I worked at is aptly named the South Pole Telescope, and it is literally at the South Pole. And so I would go there during the austral summer season to maintain the telescope, set it up for observations. And then most of our observations were taken during the austral winter. So when you're at the pole, there is 1 day and 1 night per year. So I like to say that I've spent almost a year in Antarctica and I've never seen the sun set, which is kind of interesting. But it's a base that's funded by the National Science Foundation, and the South Pole Station is fairly small. During the summer, it usually has 100 to 150 people who live there. We do have a building that's heated, so kind of very small dormitory-style rooms and a cafeteria, and then we're there to work, so we just work all the time. But it's a really interesting environment to be in. It's just a super cool place to be, and I really value having had the opportunity to spend time down there.
It sounds like an incredible experience. So you were recently at the Google Next conference talking a little bit about the work you're doing at Descartes. And one of the things that you made sure to touch on is really the types of problems that you encounter, the computer vision problems that you encounter at Descartes, and some of the unique characteristics of those problems. Can you maybe review those for us?
Sure. So the types of problems that we're working on in Descartes Labs is trying to understand the world using machine learning and using satellite imagery and other geospatial or like georeference data sets. So it's really is a big data problem, and I know that's kind of a thrown around as a phrase that people like to use, but the size and scale of the data are quite large, and because of that, it really does require automated analysis approaches, and this is where the machine learning comes in, is trying to instead of just saying we have a bunch of pictures, let's set somebody down in front of a computer to go look it through all of those pictures. That doesn't really scale to the globe, right? So that's where we take a machine learning approach where you say let's instead build an algorithms that can detect either objects or patterns, and then we can automatically scale these to large regions. So, and just to give you two concrete examples, one of the places that Descartes Labs started as a company was trying to understand corn production in the United States. So being able to measure and predict corn production over the Midwest of the United States. And then another example, just to have something concrete, is mapping infrastructure in a higher resolution in satellite imagery. So, for example, being able to simply find buildings, be able to make maps of buildings, and you'd be surprised how incomplete open source data sets are, even on basic infrastructure like this.
So the idea with that latter example is we don't have good lists of where the nuclear reactors are or the power stations or things like that. So we need to actually regenerate those lists using satellite imagery.
So some of the specific types of buildings, like nuclear power plants, are pretty well listed. But even just mapping, residential buildings and industrial buildings, and simply just knowing where they are, the best open source data set that I'm aware of is OpenStreetMap. And so some of your listeners may be familiar with that. And it's an incredible data source. But even in the United States, when I'm looking at that data set, I can go and pull it up and see entire neighborhoods that just are blank, just don't have anything filled in. And that's largely because that community has primarily been based on people hand labeling things and largely volunteer effort. And it's really impressive what they've been able to do. But being able to scale that to an up-to-date map of buildings across the United States, or even better across the world, is really just not. It's not up to the task of hand labeling all of segmenting out each building in a neighborhood. And so when you step outside of the United States, of course, the problem changes as well, in that there's just a lot less information in a lot of countries around the United States. And so by training convolutional neural nets or other machine learning approaches, we can take a first pass at being able to map out where buildings are. And that provides an incredible amount of information that would just be unfeasible to achieve in a person sitting in front of a computer screen hand labeling type of way.
I think many listeners of the podcasts may be familiar with, for example, the Planet data set on Kaggle, kind of understanding the Amazon from space. And I know for those of us who have worked through the Fast AI course, you kind of spend some time playing with that data set and learning to, automatically classify tiles that are forested from tiles that contain water features, things like that. And so we may come to this conversation and say, oh yeah, sounds easy, pretty standard stuff. Bring us to the real world. What are some of the challenges that you deal with that, the folks doing this on Kaggle don't have to
worry about?
Yeah, sure. So I come at this from my physics background, as it's all about the data and the information that's in that data. And so, stepping away from machine learning a little bit at first, you simply need to be able to access the data in an efficient way. So that's and these data sets are quite large. So when you come to a Kaggle competition, that step has pretty much already been taken care of for you. But there's a huge amount of effort in being able to get the satellite imagery and then have it quickly accessible in a way that you can incorporate into even starting to take a machine learning approach. And so this is actually one of the things that Descartes Labs realized fairly early on, was that a lot of the power for being able to work with these data sets is going to come from having a platform that allows uniform access and quick access to these types of data. So one of the things that we have done, and that's been a primary goal and continues to be a primary objective of the company, is to build out a platform that provides quick access to a huge amount of data. We do so. This is why we were at the Google Next conference. We've built out this entire platform within Google Cloud. So we pretty much don't own any hardware beyond our own laptops and are working almost exclusively within the cloud. And what that gives us is being able to host a large amount of data in a way that we can access very quickly. So that's one problem. Then a more machine learning specific problem is the ground truth question, right? So when you come to a Kaggle competition, oftentimes you have a lot of well-labeled ground truth, and basically how much ground truth you have will dictate what types of algorithms you're able to use, and then what types of problems you're able to solve. So those are at least just two problems that present themselves when you start dealing with questions in the real world. On
that first point, the platform, talk about, I'm curious what that means for you, or rather, I'm curious what all that encompasses. Is the platform, just some set of Google Cloud services that you're using off the shelf, or have you built a lot of capability on top of kind of raw, low-level hardware that you're using via Google Cloud? Walk me through what the elements of this platform are.
Sure. So it's all of the above, everything you mentioned.
Okay.
The first step is getting access to these data. So there are a number of openly available sources like Landsat or Sentinel, generally government sources, and they all have their own unique ways of accessing the data. So in principle, it's open and freely available, but each one has a slightly different format, or has slightly different image registering, or has been tiled in a different way. So the first big step is ingesting all of those data and then hosting them in the cloud. So figuring out how to access the data stream, pulling out all of that data in, uploading it into the cloud. The next step that the platform accomplishes is tiling those images across the globe. So because I'm working within within our platform, I don't have to think too carefully about how to stitch together a bunch of different images in order to make a picture that covers the region that I'm interested in. That's all handled in an automatic way. So a predetermined way of tiling the data that just simply removes one of the steps that I would otherwise have to deal with. Then there's the search question, right? So let's say let's continue working with the building model example, since that's the one that I've personally worked on directly. So let's say I want to collect a set of imagery over California to use as training data. How do I figure out which images I need to pull from the giant database? So we have a search capability that has where each image that gets uploaded has a list of metadata, and then we can, using the Google's BigQuery, this is Elasticsearch, we can search through that metadata and pull down exactly which images over which region over what time in a really efficient way, and then turning those images from whatever format, compressed format they've been saved into an actual image that I can plot on my computer and then do things with. And so this actually brings up a point that maybe we can get into a little bit later of how we think about these types of analysis. And what I mean by that is thinking about imagery instead of something you pull up on your computer and then you flip through images and kind of hand label things or look at things. Thinking about that imagery as input to algorithms, input to machine learning algorithms. And when you start thinking in those terms, it's you definitely take a different approach to how you work with that data, how you store it on disk, how you make it available.
Interesting. So, for example, is that latter point meaning, as opposed to storing the images on disk as, in a native image format, you're storing them as like TensorFlow records or things like that?
Close. That's the right idea. So we actually chose to store the majority of our data in JPEG 2000, and the reason for doing so is that format basically decomposes the images by scale, and then allows you to use the correlations between different bands. So these images, can have spectral bands, red, green, blue, near infrared, SWIR, etc. So you can take advantage of some of the fact that these bands are correlated to be able to compress them significantly.
And so when you say store them by scale, is that in the sense of like a progressive image where you've got kind of a low resolution version of the entire tile and then like progressively more detailed tiles underneath?
Yeah, so it allows you to do that without having to save duplicate copies of the data, right?
Okay.
So this is one way that we're able to zoom in and out. So on the visual side, when a person is actually looking at it, being able to zoom in and out quickly is taking advantage of that kind of layered structure of the way that the data is saved.
And then sticking to this theme of platform, you kind of talked about these 3 steps, I guess, this ingest and the indexing, and then the way you manage and manipulate these images. I don't know if I captured it exactly as the way you described it, but looking at like the ingest side, what are the different ways that you're getting the imagery? Like, are you, I don't recall if Google has a, ship a hardware box type of feature like a AWS Snowball. But is that an issue for you? Or are you mostly getting them online and landing them in cloud storage or something similar? Yeah,
it's the second option. So we're pretty much always getting them online, and then depending on most of the data sources that we're interested in are data sources that are continually updating, right? Because when you're thinking about what types of problems you actually want to use these data for, a lot of it is going to be looking for change or monitoring what's new on the surface of the Earth. And so it's important to have as close to real-time data as the sources can provide. So we're stepping a little bit outside my specific expertise, but what those in general look like are pipelines that are built within the cloud that can check for new imagery as that new imagery becomes available, pull it into the cloud, and then using parallelized compute, they can process those imagery, filter out all the metadata, get that all set up, and then store it into our cloud storage system so it can then be searched and accessed by a user like myself.
And then so from a machine learning platform, once you've got all of this imagery in place, what are some of the types of models that you're building and the specific problems that you're trying to solve?
So let's say a little bit in general about how I think about the data, and then we can talk about some specific problems. So with these data, and there are kind of 3 dimensions, sort of, that provide at least me a useful framework for thinking about how to put together analyses. By that I mean a spatial dimension, a spectral dimension, and a temporal dimension. So the spatial dimension is just where are you in X, Y, and perhaps Z position on the surface of the Earth. The spectral dimension is for each image, you may have taken data in different bands or different frequencies. So optical frequencies like red, green, blue, like a CCD camera would take, near infrared imagery. There's thermal bands. So that type of spectral information can be really important. And then there's the temporal dimension. So what I mentioned about seeing how things change over time for a given place on the Earth. And then given these three, you can combine them in different ways to address different types of problems. So to be concrete about that, usually a computer vision problem, where I've spent most of my time working, is generally combining spatial and spectral information. So you're trying to say find where things are on the Earth by looking at these images. You can also combine spectral and temporal information to say, given a place I know, so let's say like a crop field, if I want to measure how that field is doing over time, I'm probably going to be primarily using spectral and temporal information, and then obviously pull all these all together in different ways. So should I jump into a specific example or two?
Sure, please.
Yeah, so on the computer vision side, one of the places that we're kind of starting is with mapping what you can see on the ground. So this is related to your earlier comment about the Kaggle competition on planet data. So that you could think of that as basically making masks of where's forest, where's water, where are other types of things like that. Taking that to the next step would be like the building example that I said. So being able to define an algorithm that you can run over imagery, and the return result of that algorithm will be a probability map where it just says for each pixel, are you in a building or not? So this is a semantic segmentation problem, and we can use pretty standard semantic segmentation tools. And then there are also, if you don't need to segment out an entire image, you just want to say where are all of the X in the world. So an example of something we've done is found electric substations, right? So saying even in the United States, there are not comprehensive lists of all the electric substations across the United States, but you can see them in high-resolution satellite imagery. So in this case, we were working with the freely available NAPE, that's the National Agriculture Imagery Program. And so we can use an object detection approach to find where all the substations are. And if you want, I can go into more detail about what that looks like.
Yeah, please.
Sure. So let's just keep running with the electric substation example. For that one, from a machine learning approach, you need to define your data, you need to define your inputs, then you need to define the model architecture, train, and then run that model, right? That's kind of the life cycle of these types of problems. So here the input data, as I said, is high resolution imagery from NAPE. So this is either 1 meter or 60 centimeters on a side per pixel. So it's enough to actually be able to see the kind of the structure of an electric substation, where you see the wires coming off, and you see the stands that are holding all the wires and the transformers and things like that. There are enough substations that are labeled in OpenStreetMap, and so for this problem, that makes the ground truth fairly straightforward. We can just grab the locations of substations in OpenStreetMap, and for training, we don't need to know where all of them are. We just need enough to be able to train a good model. And then, using the platform, I can create images, and then I can burn those polygons that say where the known substations are into a similar target image. So I now have an image and a target pair that I can use for a supervised learning approach. And then we picked SSD model. It's a single shot multi-box detector model as our object detection model of choice. And one of the reasons for this is also kind of an interesting thing that we might talk a little bit more about is this is taking advantage of transfer learning ideas. So with SSD, so in two sentences for listeners who aren't familiar with it, the way that algorithm works in general is you take an image, you split it up into a set of predefined boxes. For each of those small boxes, you use a convolutional neural net to create a set of features. And then the final step is basically predicting whether or not each box contains the object you care about. So in my case, an electric substation. And we don't necessarily have enough examples to train something all the way from scratch, but we can take advantage of, in this case, ResNet to be able to generate those features, and then we only have to fine-tune those features and train a final classification stage. So even with a relatively small number of examples, we're able to train an effective algorithm to locate these electric substations.
And so when you say ResNet, ResNet trained on what? ImageNet or something else?
Exactly.
Okay.
Yeah, exactly. So actually, I'm sorry, I misspoke. This one is the VGG network.
Okay.
We do use ResNet in a similar context, but in other models. Yeah, so this one is using VGG as the neural net to produce features. And then we are just fine-tuning the last, or I guess training the last classification step to say whether or not each box contains the object you care about.
With VGG and ResNet and the like, typically these networks are trained, particularly the ones that are pre-trained on ImageNet and the like, are typically looking at relatively small image sizes and like 3-channel images, 240 pixel square or something along those lines. Or what approaches do you use to apply those to these super high resolution images that you have?
Yeah, so for this particular model, we used 512 by 512 images. And so one advantage, even though we're trying to use this over large regions, the Earth is still, in some sense, an embarrassingly parallel problem, right? As long as your objects are small enough that they fit into a tile, you can chop up a region into almost an arbitrary large number of small tiles. So it still works quite well, even with the constraints that you said. And then in this case, we are just taking. So you mentioned the 3 bands. That is an important difference between a lot of standard computer vision problems where you're just using a RGB image versus what I've mentioned here with satellite imagery. In this case, we are still just taking the. I think I'm using an NIR, an R, and a G band in this case. But in other algorithms that we worked on, we have used basically data compression, so PCA decomposition, things like that, to be able to compress a larger number of bands down into 3 bands that will then work with these pre-trained feature generators.
That's interesting. So in that case, you've got some larger number of bands. You've got your, I don't know if for the satellite images, the color bands, the visual bands are 3 or more, but you've got some number of visual bands, and then you've got like these infrared bands. How many total do you start with in some of those cases?
It depends on the satellite. So for example, the Sentinel satellite has 12 bands that extend from visible to near infrared all the way up into SWIR bands that are sensitive to thermal emission. So it can vary a lot.
So you've got 12 bands, and you're able to use PCA or some kind of alternate projection of these bands down to 3 bands, and yet a model that's trained on kind of visual ImageNet objects still works?
Yes and no. It's
surprising. I mean, because I'm imagining that these visual, I guess in one sense, like the result of this PCA thing, I'm not imagining that to really mean anything visually, right? And so your model that's been trained on this highly visual data, in one sense, I wouldn't expect to work. On the other sense, like all it's doing is learning a bunch of different kinds of patterns. That's what you're counting on, is that it learns a bunch of different types of patterns that themselves aren't necessarily visual. So maybe it should work.
Yeah,
So
exactly. And it's a lot of trial and error, right? It's a lot of like, hey, this I don't know, this might work. Let's do a small test and just see what happens. And in some cases, this type of transfer or compression has worked well. And then in other cases, I think hopefully we'll talk about GeoVisual Search in a little bit. There was insufficient, and we had to do some further fine tuning to be able to get effective features. So it just, it's a lot of trial and error, and a lot of simply digging into the data and doing a few tests, seeing what works, seeing what doesn't, and then moving on from there.
you mentioned that to get your ground truth, you start with this OpenStreetMap data that has identified some number of electrical substations. How many approximately are there that are identified?
So in the ground truth set that I ended up with, I had a few thousand.
Okay.
So that kind of gives you an order of magnitude.
Yeah. So you got a few thousand of these electrical substations, and you said you burn them into the images, meaning
just simply saying that the output from OSM is a polygon that has lat long coordinates to trace out a boundary, and I'm just simply turning that into an actual image of zeros and ones within inside that polygon and zeros outside that line up with the corresponding image from the satellite.
And is that type of training data arrangement wherein you've essentially colored on a pixel by pixel basis, is that kind of what SSD is looking for?
So then for SSD, there's one final step of then drawing a bounding box around the ground truth object. And so I guess we probably could skip the burning the raster step to make it slightly more efficient. But then the actual training is done against the coordinates of I guess at that point they're actually in pixel coordinates. So we do need to go through the image to get the pixel coordinates of the bounding box for the object of interest. Did that make sense?
Yeah. I mean, it sounds like you could potentially do some kind of math going from a polygon from the OSM data set to pixel coordinates, but the way you did it is by just manipulating the pixels on the image themselves.
Yeah, that's right. And with a lot of these things, it's a question of where do you invest your time?
Absolutely.
And so something like that, you could probably make that better. But there's 1,000 other things that are more important to put my time in at my desk into.
So you've trained this model, and I'm curious, are you with, you mentioned some places you use VGG, other places you use ResNet. Are you, is it kind of for some projects have you built up an intuition around where you use specific things that works, or is it more like kind of looking at the rings in a tree, like this project is older, and so you use VGG, which was state of the art at the time, and now if you were to do it again, you'd use ResNets?
Yeah, there's a lot of that, right? Exactly what you said. You build up models as you go, and then as new tools come online, then depending whether or not it's worth going back to fix up a model will dictate whether or not you go back and try out new tools or new feature generation. I hope we'll talk about GeoVisual Search in a bit, and that's an example of that where we've done something that's worked pretty well, but then are now in the process of going back, using new tools, using new data, trying to make it better.
Okay, well, let's do that. Before we do that, have we covered all of the important bits on the substation identification?
And maybe one last thing, just because with this being the Google Next series and relating to the cloud, an important part of these models is once you're done with the model, you need to be able to run it efficiently over large regions. And so it's not machine learning specific necessarily, but it's definitely cloud related. So as I mentioned a few minutes ago, the Earth is somewhat of an embarrassingly parallel problem where you can just chop it up into a lot of little pieces. And this really lends itself very naturally to a cloud environment. So once we have a model, then let's say I want to run it over the United States, I can just grab all of the imagery that to cover the entire United States, chop it up into little 512 by 512 pixel pieces, and then hand a set of those and the model to a worker in the cloud, and then I can spawn effectively an arbitrary number of workers to go process all of these data through the model and then save those results directly to the cloud. So just by working in that highly parallel fashion, that's how we're able to automate analyses and run them in a reasonably quick amount of time. So like I mentioned the building detector. I was able to run that over the entire state of California kind of overnight. And so I come back and work in the morning and I have a map of all the buildings across the state. So that's just the kind of the final piece of the model life cycle.
And even with that final, that specific piece and, the constraints you mentioned of taking this model, handing it to something that lives in the cloud and having it run in a distributed fashion. And even within the confines of Google's cloud offerings, there are still probably I can think of 5 ways off the top of my head to do that specific thing. Like, do you get involved in the infrastructure pieces of putting that all together? Or maybe more generally, how have you architected this distributed execution or training? Is it is it one of the higher level, the machine learning engine type services, or is it all running on just cloud engine workers that you guys build up and manage, or is it running on Kubernetes?
Yeah, so the engineers on our team have built up a system in Kubernetes that are using primarily preemptible VMs, and then we've written our own task scheduling software that will, we've written our own task scheduling software that will launch jobs into preemptible VMs. All of the work environments, so capturing the code, and then all the different dependencies, things like that, using Docker, and then inside of Kubernetes. And so then you can set up an environment in each of those workers, run the code, save your results to the cloud, and then break that all down. So it's all Kubernetes based. We're now working on getting Istio, which is one of the new monitoring packages out of Google, to be able to monitor all of these processes in an effective way. And then we're not using the ML engine yet, but it's something that we're looking into.
And are you also looking at the Kubeflow package for Kubernetes?
Yeah, so that's also something that we're looking into at this point. So far, we're basically running our own models. We're largely Keras models, but yeah, Kubeflow is something that we're starting to look into now.
How long has the platform been around? How long have you been working with Kubernetes?
So the company in total has been around for about 3 years. So we're a pretty new company. And I'm not on the engineering team, but we've been working with Kubernetes for a while. So I think most of that time.
Cool. Yeah, we won't drill into necessarily the Kubernetes details here, but I may be interested in talking to someone on the engineering side as well, for
absolutely.
Background. We talked through the substation detection problem, and you've been chomping at the bit to tell us about the GeoVisual Search. Tell us about that problem.
Sure. Yeah. So this, I kind of chomping at the bit just because I think it's cool and interesting and a little bit unique. So the idea with visual search is to be able to click on anywhere on the Earth and then be able to see other areas that look like this. So at a high level, you can think of it as kind of a generalist model that hasn't been trained to find anything specific, but is able to search over a large region for lots of different types of things. So then the way it actually works under the hood is kind of cool. So maybe I'll take a few minutes to walk through that now.
Yeah, please.
Cool. So the way it works under the hood is fairly similar to many of the ideas that we've been talking about so far in this podcast. Take a set of data. So in our first pass, we've worked with either NAPE that I've mentioned before over the United States, or composite of Landsat over the entire globe. chop that imagery up into a bunch of 128 by 128 images, and then use a ResNet-based feature generator to create a set of features, and then simply search for similarity between features for each tile. So when you click on a tile, it's doing a similarity search to say what other tiles have similar visual features. So this touches a number of the things that we've already mentioned on this podcast so far. The first one being whether or not the ResNet features are sufficient. So in this case, we found that the features that are generated by ResNet were not good enough to be able to have a really clean visual search. Mm-hmm. And so we did actually do some fine tuning of those weights, basically. For NAPE, where it's high resolution enough to be able to see a lot of objects, we took an approach of grabbing a bunch of different objects from OSM, again, from the OpenStreetMap, and then doing a supervised fine-tuned training of the features to be able to match to OSM objects. And that just kind of cleaned up what types of features that the network was generating.
And so specifically to drill in on that point for a second, what you mean is that the features that the pre-trained, presumably on ImageNet, model was had, as opposed to the architecture itself. You weren't ever training from scratch. This was all, we're still talking about pre-trained ImageNet models.
Exactly. That's exactly right. So yeah, taking advantage of all of that computation and pre-training that went into creating the ImageNet-based ResNet weights, and then just fine-tuning those.
And I'm curious, can you provide us some scope or order of magnitude of the fine-tuning effort, just to get a sense for, how much you benefit from someone else doing the heavy lifting of training ImageNet?
I don't really have a good way of quantifying that.
Okay.
At the moment. Yeah, sorry.
So you start with the pre-trained ResNet model on ImageNet. You fine-tune, and then when you talk about using the features of this ResNet model, are you basically chopping off the classifier at the end and using that last layer, or are you using intermediate layer activations or something like that?
Yeah, so we're basically just chopping off that last classification layer. And then an additional step there is, if we store all of those features, the feature numbers in their full size, that would take up a huge amount of disk space. So we've actually binarized those features by injecting a bunch of noise at the end of the training process to basically force those features to choose between either 0 or 1. And then in the in the final network, we threshold it. So the output of running a tile through the trained network is a list of 512 bits, 0 or 1s. And that's at the cost of basically the precision of being able to differentiate between. So we lose a little bit of differentiation power, but we gain a lot in both speed for the search later and in terms of having it take up a reasonable amount of disk space.
Can you elaborate on that process, the noise injection process, and how that translates to allowing you to isolate these individual pixels?
Yeah, sure. So basically at the last step, we injected noise during training with an amplitude that was comparable to the width of the layer's activation function. And so this means that the network needs to basically either decide, the activation needs to either be 1 or 0. Otherwise, there's enough noise to kind of destroy the information that the layer is trying to pass on. So it forces the network to learn to output either very close to 1 or very close to 0. And then once we have that, then we can just, once that's trained, then we can, in the final model, we can just add a thresholding step. Does that make sense?
And you're injecting that noise at the last layer itself, as opposed to in the input by manipulating the image? Or
that's right.
Is it at the, okay.
Yeah, it's just at that last step.
Oh, it's interesting. Is there a name for that technique?
Not that I'm aware of. There very well may be, but
okay.
I'm not aware of a specific name.
Okay. At that last layer of ResNet, how many features are there?
So we're ending up with 512 features per input image.
So what you're trying to do is not, you're not trying to necessarily reduce the number of features. You're trying to basically compress them to on-off.
Yeah, that's
okay,
right.
Got it.
Yeah, exactly.
Okay.
And then just to complete, because it's also an interesting idea, for the Landsat data set, this same fine-tuning process, but instead of using OSM, there aren't really enough useful information in OSM across the entire globe. So we took an autoencoder approach, basically, and used that as a way to fine-tune the satellite imagery feature generation for the Landsat data set.
And what's the relationship between the fine-tuning process and OSM or the auto? We'll get to the autoencoder, but how does the OSM data help you with the fine-tuning?
It just makes the features that you're generating more responsive to the types of things you see in satellite imagery. So kind of exactly what you mentioned earlier, where ImageNet is trained on a bunch of pictures that may or may not have the size and shapes of the types of things that you're interested in satellite imagery. This just allows us to fine tune those weights a little bit to make them more descriptive about the types of visual features that we see, in satellite imagery.
So does that mean, you've got satellite imagery in your original data. Is what you're doing, are you using OSM to give you landmarks so that you can train on specific tiles that are interesting as opposed to training on a bunch of ocean or something like that? Or is it more nuanced than that?
It's partially that, but it's more recognizing the fact that a overhead picture of a city park and a golf course doesn't look exactly the same as a picture of a cat or a dog. And so the features that a network learns to consider interesting from one of those images won't be exactly the same as the features that a network learns to consider interesting from the other one. And so it's really more accounting for that type of difference, knowing that we're going to be applying it to satellite imagery. So trying to just fine tune a little bit what information the network is pulling out of those images.
Okay. So you're doing this before you take off the classifier, and you're training on OSM tiles because you've got labels for them.
Exactly.
Got it. I missed that part. I was thinking we'd already chopped off the classifier. And so how do you use an autoencoder to do that? You're basically doing it in more of an unsupervised kind of way?
Yeah, exactly. That's right. So Landsat imagery is a lot lower resolution, 15 meters per pixel instead of 1 meter per pixel. So the labeling from the OSM simply wasn't as useful. And then additionally, there weren't as many labels around in other continents around the globe. And so we still need to, we use an autoencoder to basically compress those compress the final ImageNet features down into the same number of 512 feature bits. So in that case, the autoencoder we're basically using it as a compression algorithm to get from the output ImageNet features to the small number of binary features that we want to use for the visual search.
Cool.
So then that result of that process is we've now tiled up the United States and the Earth into small tiles, and we've trained a algorithm to create visual features for each of those tiles. And so now the search part of the visual search comes in. So the basic idea there is you want to look for tiles that are close in feature space. And so we took a kind of a two-step approach to making this work. First, we used Hamming distance as kind of a first pass filter. So this is just simply looking at the difference, just lining up the bits and looking for differences between bits. And that allows you to zoom into a smaller number of candidates that may be visually close to the tile that you're searching for.
Mm-hmm.
And then as a final step for the Landsat data, that first step was enough to limit it down to where we could simply do a direct search of just comparing bit by bit, a brute force search over all of the close images, and then return the image that's closest in feature space. For the NAPE data set, which starts with about 2 billion of these little tile images, a direct search works, but it's too slow for interactive use. So we needed to do something a little more creative to be able to make this so you could click on something on a website and have information come back to you in real time. And so we used an approximation method called bit sampling, which is basically takes a set of 32 hash functions, and then it hashes sets of bits to reduce down that 512 feature bit vector into smaller chunks, and then looks for images that have similar outputs of that hash function. And then you can do a brute force search of that second filtered set of images. Did that make sense?
It does. I'm curious whether the notion of using some kind of projecting this feature space into some kind of embedding layer, does that make sense in this context? And using like the distance in an embedding layer to do image similarity?
I think that approach could make sense. Yeah, this type of search is basically what we landed on first, but an embedding approach could also work well.
Okay. Interesting.
So then the output of that is we now have a search capability where you can click on a little tile and get back results in other tiles that look visually similar, basically in real time. And it's publicly available on our website at search.descarteslabs.com. You can go play around with it if you want. And so it forms it's as I said in the intro, it's kind of a generalist model that's looking for things that look visually similar. And then for some types of problems, that's enough. For other types of problems where you want a higher precision recall in the objects that you're detecting, or the objects aren't quite as visually striking, then you need to take a more expensive, more standard computer vision approach with like the electric substation, as I mentioned before, for example.
I'm curious with the GeoVisual Search, have you developed a way to characterize the accuracy of the end-to-end process? Like the performance metrics that you would typically look at for a training process are, don't really apply because you're kind of shifting the use domain. And I'm wondering if there's a way to measure the extent to which this feature similarity maps to what people think is similar or what people want to see. Like, is it figuring out tiles that have the same number of buildings, or tiles that have some, maybe there's something that's not really, that doesn't jump out at us that causes feature similarity, but it's not, it's not necessarily what an analyst wants to see when they're clicking around. How do you characterize that performance?
So we haven't done anything quantitative in what you described. You certainly could say, I have a class I care about. Let's see whether or not visual search, you could calculate a precision recall for if you had basically a labeled data set that you could check against.
Right.
Here, it's we haven't done that type of quantification of the process, and because that'll also depend a lot on which object you choose. For example, so we've thought about this more as just kind of a general first pass search rather than a quantifiable like precision recall tool.
Right.
If that makes sense. But yeah, it's definitely the type of thing that you could do. We just haven't performed that exercise with any specific examples.
And you mentioned that's once a user cares about that type of precision, you would lean more on the type of process that we described earlier, where you're modeling around a specific type of entity or object. And it sounds like, presumably what you have found is that, when people click around in this map, they tend to get results that are appealing to them, that satisfy the base promise of the system. Yeah,
exactly. So it's kind of an interesting, I think of it as an interesting starting place. Or you can even say, if I'm thinking about investing time and therefore money into a more exact model, are there enough features that will look visually distinctive, do I have a good chance of being able to build an effective model? But then, for a solution where you really want quantified precision, then taking one of the other approaches, either object detection or semantic segmentation, and building a specialist model for the exact thing you're looking for has almost always been much more effective.
Great. Well, just as we kind of wind down, I appreciate you being flexible with time here. We went over a little bit, but this has been really interesting. Are there any other things that you'd want to leave folks with?
Thanks for having me on. It's been fun to discuss these things. And if people want to play around with some of these things, go check us out.
Awesome. Well, thank you, Kyle. Thanks so much for taking the time to chat with me about this stuff.
All right. Thank you.
All right, everyone, that's our show for today. For more information on Kyle or any of the topics covered in this episode, head over to twimlai.com/talk/173. As always, thanks so much for listening, and catch you next time.